Hello everyone, I am Bogaerts from Ghent University in IMEC, and I'm happy that I can talk to you about the interesting subject of programmable photonics. Now, what's in the word? What do we mean when we say something is programmable, and what do we mean with photonics? I guess for most of us, the word photonics is quite obvious. It has basically anything to do with light, how we manipulate light and preferably manipulate light on a microscopic scale. With programmable, yeah, we're also familiar with that concept. We want to manipulate things in software. So if we bring these two together, then basically with programmable photonics, we mean manipulating light in software on a very small scale. Now there's a good reason why we want to do that. Light contains information. Now, what kind of information can we encode in light? Well, of course, if you have a beam of light, the total power can be switched on or off. So that's information. But a beam of light also has an intensity profile, a phase profile. It has a wavelength. It has polarization. So there's a lot of information in light that can be manipulated. Now, if we want to manipulate light on a larger scale, it quickly becomes a problem. Especially if we use free space setups like this one on an optical table. At some point, it really becomes unmanageable. It doesn't scale well. And of course, as we all know in this audience, this means that we can go to chip to go and integrate light on a much smaller scale. And with photonic integrated circuits or optical chips, we get all the type of benefits that we also experience with electronics chips, in the sense that we can get much more complex circuits, better performance, at a smaller scale, lower power consumption, and eventually a lower cost. Now, photonic integrated circuits, as you well know, are not the same as electronic circuits. We find different functions, in particular functions like the generation of light with lasers, modulators, wavelength filters, photodetectors, etc. Now, if we look over the past 2 decades, then we see that photonic integrated circuits have systematically become more complex, and we're now looking at photonic circuits to the order of 10,000 and maybe even 100,000 of components in the same circuit. Eventually, we're going to a density of 1 million circuits on a square centimeter, and we see a steady exponential increase, like in Moore's law. Again, combining all these different functions like light sources, waveguides, filtering, modulation, and detection. Now, photonic integrated circuits, to perform all these functions, you need different materials. And typically the best materials for each function tends to be quite different. So we see this wide variety of optimal materials for all these different functions. And if we look at the landscape of photonic circuits today, indeed we see that all these materials are some way represented. But the interesting curve is the one here at the bottom. This triangle at the bottom represents silicon. Now, silicon does not come out as one of the best materials for photonics. It's not a good light emitter, it's not a good detector for infrared wavelengths. So why would you use silicon? Well, for the good reason why silicon is also used in electronics. We have this infrastructure that allows us to process silicon waveguides and silicon photonic structures to a very large scale in a CMOS fab. And that allows us to make very complex functions on complex chips at a low cost and potentially scale this to high volume. Now, an example of such a silicon photonics platform, and there's plenty of them now today in the world, is for instance IMEC's ISSBO platform, which contains waveguides, modulators, detectors, filters, grating couplers, edge couplers, thermal tuners, and even with transfer printing we can integrate lasers. Now, there's a question though. Even with a complete platform like that, can you actually scale this to high volumes? And this question is important because high volumes for photonics people mean something very different than for electronics people. The volumes for photonic components are quite small. Now, if we want to go to high volumes with photonics, we will need, just like with electronics, have photonics chips that are used in a variety of applications. But today that is not the case. Today we see mostly that photonic chips are used in devices like this, transceivers, which is basically saying that you can also only use electronics in devices like that, which is calculators. But that's not what happens today. even though photonics is only used in transceivers, electronics is used in a wide variety of applications, from every most simple toy to cars to airplanes to headphones to microwave ovens to cameras. You find electronic chips everywhere, while photonic chips today are only found really in fiber rigs. So where are all the other photonic chip products? Well, we know indeed optical fiber communication is driving the market, and especially data centers. And with the advent of AI applications, this push is even stronger. Optical communication is the main driver for photonic integrated circuits. So the silicon photonics transceiver market is now really pushing to like high bitrate, 800 gigabaud or gigabit per second at 100 gigabaud data rates. And this is really pushing the market. However, if you look at the market studies and the market predictions, even though today you see that in the market it's mostly dominated by datacom, the predictions are several years in the future that a large fraction of the market will be taken up by other applications, especially in sensors, consumer health, and maybe even LiDAR. But if you look today, where do we find these? Not in a lot of places. You have some good examples, like for instance, this is an example by Analog Photonics, a LiDAR chip. It's a quite complex silicon photonic circuit. It really shows what the technology can do. But you cannot buy this as a product. Here, this is an optical gyroscope by Anello, a US company. That's one that you actually can buy. You can buy this gyroscope and use it in your applications. Or another example of a very fancy application, this is a biomedical device that allows you to monitor your pulse wave velocity, essentially a metric for cardiovascular health. Can you buy it today? No. Actually, if you would look and Google on the internet, there's very few products that you can actually buy that contain a photonic chip, and that at the same time is not meant for communications. There might be others, the list is not complete, but there's still very few. So the question can be asked, if we have only so few optical devices, why is that? Why is photonics not breaking through in many more applications? Because we have fabrication technology, we have ideas. There's been thousands of papers proving any concept for a sensor in an R&D lab, but it's not yet there in a product. And one of the key reasons why this is not is because it takes too many iterations to get it working. We don't have, in photonic development, very fast iterations. We don't have rapid prototyping. So we need more design tools that are better at predicting how photonic circuits work. But we also need rapid prototyping. And that's, for this long introduction, where I come to programmable photonics. If you look at a product development cycle, based for instance on a custom chip solution, which is what most photonic products consist of today, you have to design a chip, fabricate it, test it, and package it. That takes you more than a year. And if something goes wrong, you have to redevelop it. Now, if you compare that with a photonic chip solution that is based on design iterations, it goes faster. And if you can do it based on a programmable chip, it's even better. Because with a programmable chip, you can accelerate these cycles in a matter of days by just reprogramming the functionality on the photonic chip. Now, this is a model that we have seen and in electronics that works very successful. If you look at the evolution of electronics and electronic chips, they started out with very simple transistors, but today you can buy these very complex microprocessors and these field programmable gate arrays, FPGAs. Photonics has gone through a similar evolution and has grown in complexity, so we see now today very complex silicon photonics. But unlike electronics, where you have both application-specific chips and programmable ICs, in photonics, all the chips are application-specific. We don't have programmable photonics today that you can buy for rapid prototyping. And in electronics, this really works well. You have microcontrollers, you have FPGAs, digital signal processing. Essentially, you have hardware that you can, in software, reconnect and redefine its functionality to basically build a new function. In photonics today, we really need something similar. Programmable photonics Some people call it photonic FPGAs, reconfigurable photonics, photonic processors, universal photonic circuits. Essentially, photonic integrated circuits that can be reconfigured in software to perform a variety of functions. Now, what would this look like? Well, you can come up with like a simple black box figure. It's essentially a chip that can handle optical signals going in and out, and also microwave signals going in and out. So this is simple to draw. How would you actually build this? Well, let's go to the very basics. We can basically take such a processor and translate those functionalities to a photonic chip. Let's start with the optical functions, so let's leave the RF functions out for the moment, and let's see how a typical optical input, optical output chip would look like. I make it as simple as possible. You basically have an optical filter. Your light comes in, it gets filtered, your light goes out. That's a very, very simple function. You can input with fiber couplers or grating couplers, you can do that with edge couplers. The details of the components doesn't matter that much. The point is that this chip would process an optical signal. Now, we also know other types of optical circuits, typically with active devices, for instance, a transceiver, a transmitter with a laser and a modulator, a receiver with a photodetector, again using fiber interfaces. Now, in this case, this chip also doesn't process optical signals, it also processes high-speed electrical signals, because your modulator is modulated with an RF signal, your detector outputs an RF signal. Now, you don't necessarily have to go to a fiber. You can also work on the chip itself. You can also integrate this passive function, and you can shortcut the fiber, so you only have now a photonic chip, but without optical signals going in and out. This is a black box photonic chip that operates as a microwave processor. And indeed, if you now make everything tunable, we have a kind of programmable signal processor that can be reconfigured by playing with the states of all these tunable couplers and phase shifters. If we now, to this chip, add additional inputs and outputs, you can inject or extract optical signals and inject and extract microwave signals. Essentially, you have here a programmable microwave and photonic signal processor. We've built such a chip. This is the footprint, so you see modulators, lasers, programmable filters, and of course electrical bond pads and grating couplers to connect to the outside world. And this chip, then we packaged it with RF connectors and optical connectors and wire bonds to the driver electronics. Now, if you take this chip now, you can use it indeed as an optical filter, just like this most simple example that we made before. This filter, of course, is fully programmable. You can completely independently control all the states of the individual rings, building a higher order filter with a tunable passband and a tunable resonance. But you can use this filter also to filter microwave signals. So in this case, instead of an optical signal, we use the laser and the modulator to generate a microwave signal on an optical carrier, and then use the optical filter to filter the microwave and a photodetector to convert it back into the microwave domain. And here too, we can fully configure the response of the microwave filter, creating a low pass filter, a high pass filter, an equalizer, and a passband filter. This is just an example that with photonic circuits, as long as you add enough tunable elements, you can really do the signal processing. You can do optical filtering and microwave filtering and a lot of other functions that I didn't go into detail about. Still, this optical circuit is nice, it's programmable, but it's still limited. Light flows in just one direction, and you can only execute the functions on the chip in a specific order. So we want to have more control over the flow of light. Now, this is taking programmable photonics one step further. What if we now build a chip where we can control the flow of light? And the typical example of such a chip is one of these waveguide meshes, these forward waveguide meshes, where light flows in from one side, from the inputs, and then goes all the way to the outputs. Now, to control the flow of light and the distribution of light in such a circuit, we make use of optical gates. Optical gates are essentially an element with two optical inputs, two optical outputs, and by electrical tuning you can control how the two inputs are coupled and what their relative phase delay is. So to implement this, you only need two types of functions. You need some form of tunable coupler, and you need some form of electro-optic phase shifter. And in practice, you can do it even with just phase shifters, because a tunable coupler can be implemented as a Mach-Zehnder interferometer with a phase shifter in there. So, and then you need a second phase shifter to basically control the relative phase. So this is a very interesting component, because with just this component we can make very, very powerful photonic circuits by just programming them. To give you an example, if we basically take one of these optical gates, so with a phase shifter and a tunable coupler, we can reconfigure this optical gate to couple all the light to one output, irrespective of the relative intensities and phases at the input. We can just simply do that by adding a photodetector to monitor it, and then a feedback loop to minimize the intensity in the detector by tuning the phase and by tuning the coupler. And with those two control levers, we can essentially just reduce the power of the light in the detector, meaning that all the light will actually go to the other output, to output 2. And now we can cascade such gates to make circuits that do the same thing but with a larger number of inputs, essentially just reducing first the light in output 1 using the detector, then reducing the light in output 2 as well using the second detector, and then eventually using eliminating the light in output 3, so that after the light has propagated through this circuit, all the light ends up in output 4. Now this is a very simple technique, because we don't need to do any computations, we just need to minimize the power in the detector, and this circuit can actually adapt itself to different configurations of the inputs. So an example is something that we implemented already quite some time ago in our group in Ghent. That's a circuit with 4 inputs, and basically we can monitor the state at each point in the circuit and adaptively optimize the state of the circuit with a feedback loop to keep the input or the power at the output maximum at any given time. And that's the blue curve you see at the top right. Now this is a small scale circuit. You can scale these circuits up to much larger circuit. This is an example a bit later from a group in MIT, where you have 26 inputs, 26 outputs. And the nice thing of these circuits is that by just mapping these inputs on these outputs with these programmable optical gates, you can do quite some really interesting functions. And in particular, if you represent the input amplitudes and the output amplitudes as a vector of complex numbers, what this circuit does in real time is perform a matrix vector multiplication, which is a very useful function for everything that has to do with pattern recognition, linear optics or linear operations, especially in artificial neural networks. This is an operation that's used quite a lot. So it's not a surprise that this type of functions, this type of circuits, is now used a lot in exploring new efficient ways to implement neural networks and even quantum optic applications. But in a way, even though it's powerful, it's again limited, because light can only flow from left to right. There's no delays. The response of this circuit is more or less wavelength independent, so filtering is not part of the circuit. What can you do to alleviate these shortcomings? And this brings me to the third class of programmable photonics, which is recirculating meshes. Recirculating meshes basically use the same type of optical gates, but now we organize them in loops. That can be square loops, hexagonal loops, essentially just ways, ring resonators kind of, that couple together, and the coupling is entirely tunable thanks to these optical gates. Now if you take such loops, you can now basically control the flow of light through your circuit by just changing the state of every individual element in your circuit. So you can switch from cross to bar state and reroute your light through different paths. You can do that for multiple paths and even route paths through the same coupler. You can also use crossings. You can do distribution of light by switching them to partial state. And if you can split your paths of light, you can also combine them. So now you see that we have an opportunity here, a way to build interferometers on our chips. If we add now a delay by just routing the light through a different path, we have the basis for an optical filter. We have a Mach-Zehnder interferometer. And as you can also route your light in loops, because the loops are a native part of the circuit, you can also make ring resonators. So this is a really, really powerful method to build large-scale photonic circuits. Now we've implemented such a circuit. This is an example of a small chip, which we call NOVA. It has 7 of these hexagonal unit cells, and the unit cells are of course coupled together with these optical gates. You see an example of such an optical gate, which consists of a Mach-Zehnder interferometer with 2 heaters. A relatively simple architecture. The circuit has 24 ports which are coupled to the outside world through fiber couplers. Of course you need everything to work, so all these 84 heaters in this circuit need to be driven by electronics, and you see that the electronics in this case is this big stack of off-the-shelf current drivers which are connected to the small chip you see on the right of the picture, and at the top you see the chip embedded in an epoxy connected to a fiber array. Now if we take this chip, we can now configure its states. For instance, we can configure a ring resonator, and we can tune that ring resonator to achieve critical coupling and try to maximize the Q factor in critical coupling. This gives us a quality factor of 55,000. And from that we can compute what the loss is in our individual devices. So with a bit of computation, we can come to a number of 1/4 of a dB, 0.25 dB per optical gate, which is actually not a bad number for a circuit like this. Now you can do other functions, of course. You don't have to stick with a ring. You can do, for instance, a splitter tree by just switching couplers into a partial state. And in this case, this is a 1/8 splitter tree. We can very nicely balance the power in all the outputs. We can also implement delay lines by just routing the light through incrementally longer paths with about 4 to 5 picoseconds delay per optical gate, which corresponds to its optical length. You can do filters, not just single rings, but also multi-ring filters. For instance, this is a coupled ring resonator, where in the different curves, you see that we change the coupling between the rings to get a different passband. Or you can even do higher order filters based on Mach-Zehnders. This is a 2-stage lattice filter intended or designed to be like a 50% passband filter. Now these are just examples of what you could do with such a circuit. But of course this is just passive functionality. You can make such a waveguide mesh with optical inputs and outputs, but essentially it would only do the routing and the filtering and the splitting of the light. If you want to make really useful signal processors, you need to again introduce all these active functions that we started off with. You need the modulators, you need the detectors, and maybe even amplifiers and lasers, etc. So a full-scale programmable photonic chip would look a bit like this. So you have the mesh in the middle, you have your modulators that act as microwave inputs, your detectors that act as microwave outputs, and then maybe some specialty functions which are also located on the periphery. And at the center, at the heart of this mesh, is of course this optical gate, this 2x2 circuit that mixes the inputs and the outputs. Now there's a couple of challenges if you want to implement good optical gates. Optical gates, because you have so many of these, they also need to be very good. So they need to be small, they need to be short optical length, they need to have low optical loss, low power consumption, compatible with the CMOS drive voltage, fast, preferably megahertz or like microsecond scale, no crosstalk. I mean, if you drive one gate, it should not affect the next gate, and of course integrated with all the other functions on the chip. Now today this is a challenge. There's no technologies that actually meet all these criteria. You can implement optical gates in many different ways with heaters, with carriers, with MEMS devices, liquid crystals, etc. But none of them are perfect. Let me give you some examples. For instance, first of all, you can take all these technologies and kind of put them on 2 axes. First, the speed of the effect, how fast can you actually switch a gate on or off? And how strong is the effect? And that's a measure for how long does the gate need to be, or how much power do you need to put in to get an effect. Now, today the workhorse for all of these circuits is heaters. If you want to make a complex photonic circuit today, you typically use heaters. They're kind of crude, they're not very sophisticated, but they're very easy to implement. For instance, if you have a silicon photonics platform, you can make a heater in the form of an electrical resistor that is either in the metal layers or in the silicon layers, but it's very easy. You just run a current through it and you basically get heat, you heat your waveguide and you get a phase shift. In order to make them more efficient, well, you can add some tricks, for instance, adding undercut, removing the substrate so that the heater is locally thermally insulated, which makes it a bit more efficient, which then makes it also a bit more compact. For instance, the heaters we use in our circuit, they are not the most efficient heaters in the world, but they still do their job with a power of less than 8 milliwatts to induce a pi phase shift. And they work quite well. They're quite compact. They're like 50 microns long. And the loss is not that dramatic. Now, they're not perfect. So we also in parallel are looking into other opportunities and other capabilities. For instance, liquid crystals. These are kind of interesting material because they have a very strong birefringence and therefore you can induce electrically a very strong optical effect. But how do you integrate it with the silicon photonics platform? Well, in our case, we basically already have a module in our platform where you can open up the backend, so you can edge back the silicon and the oxide layers that are on top of the waveguides. Now, then you need to get the liquid crystalline. So what we do is essentially just inkjet printing. We locally deposit liquid crystal in our platform. So now we have a very local deposition of high birefringent materials. And if we now engineer the waveguide cross sections that you have a waveguide and an electrode, so that you can basically change how the liquid crystal orients itself close to the waveguide, well, you can get a very efficient phase shifter. And that's essentially what we see here. And this was published like a year and a half ago in Optics Materials Express. We have these liquid crystals here locally on the chip, these little colorful rectangles. They are embedded in a Mach Zehnder interferometer for characterization. And then you see that for a 5-volt drive current, for drive voltage, which is an alternating voltage, so you have to modulate it, we get more than a 2 pi phase shift. And actually more recent devices have increased this efficiency to more on the order of 4 pi for a 5-volt phase shift. So this is a really, really promising result for these devices. And they're also very compact. You can shrink them down to like 50 microns. In this example, it's 100 microns, but they can be much shorter. So that's similar to the heater that we have in terms of optical length. That's very, very useful. Now, an alternative to this liquid crystal that I just want to cover briefly is microelectromechanical systems, or MEMS. What are these devices? Well, they're essentially freestanding silicon photonics devices. So in this case, you have a waveguide, but the waveguide has been underedged, so it's suspended. And next to the waveguide, you have this thin beam of silicon, which is indicated here in blue, which is also suspended, but can also be moved or can be pulled away by this shuttle. It's suspended by these purple springs, and it can be pulled away by this comb drive on this movable shuttle by just applying a voltage. Now this is very interesting because this is electrostatically actuated. This is a DC voltage applied on this comb drive will actually pull this shuttle away, and it does not require any current and therefore does not require any power to maintain its state. And if you run the mechanical, optical, electrical simulations on this device, then you end up with a design that gives you a pi phase shift for roughly 30 volt of actuation. Now in practice, because of the built-in stress of the silicon on insulator layer, the device is even more efficient. So we get this pi phase shift for about 20 volts of actuation, which is really, really good because the voltage might be relatively high. The power consumption is in the order of nanowatts. Now, of course, with these devices, you have to be careful. These are MEMS devices. These are mechanically fragile devices. So we added to this process an additional process to hermetically seal these devices in. As part of the Morphic and Formic projects, we basically, our partners at KTH, built this process where you have these silicon lids sitting on top of your devices, encapsulating them and protecting them from harm from the outside world. While still at the same time, and you can see this here in this SEM pictures, keeping your grating couplers and your metal bond pads accessible for the users and for the packaging. Now, this is just some examples of optical gates that you might be able to implement. These processes are not yet mature. And that's a bit of a problem, because as long as these individual gates are just in an experimental stage, we have a problem to scale this up to large circuits. Because in a large circuit, you need many of these gates, tens, hundreds of these gates. And all of these gates need to be electrically connected and they need to work. Just to give you an idea of the scale, this is an example of a MEMS device circuit, part of a larger programmable photonic circuits, where you can see in each of these kind of Y-shaped subcircuits 3 tunable couplers and 3 phase shifters. And each of these needs to work. And not just here in this one element here, but if you zoom out, you see the scale of the circuit. This is a circuit that contains thousands of individual devices, bends and waveguides, etc. More than 700 of those need to be actuated, and on top of that, another 200 photodetectors. That's a lot of devices that need to be broken out to the outside world. So not only need all the gates to work, you also need to interface all the gates to the outside world, to their electronic drivers. That in itself is a massive packaging challenge. And especially if you're doing prototyping, coming up with packages that support this large number of optical and electrical elements is very hard. Again, this is something that we built in the Morphic project in Europe. This is mostly designed by Tyndall. This is a ceramic interposer, 21 layers, so it's a very complex interposer that can interface up to 3,305 electrical connections to the outside world. So if you have a photonic chip that uses a standard design template for these 3,305 connections, you can basically put it on this interposer, and then the top one, the chip side, is shown on the right. The bottom side of the interposer is shown here behind me. So these very dense interconnections are broken up into a much wider space, which is compatible with a printed circuit board and which you can use for with standard packaging techniques. So this is a way, starting from our photonic chips, we can put gold stud bumps on them. We then solder jet the balls on the interposer, do a flip chip of the chip on the interposer. So you see the silicon photonics chip in black sitting at the top right. And then the interposer, the bottom side, has all these wider space connections. This can be put on a printed circuit board either with a connector, a spring-based connector, or with solder balls. So for that, you first take the bottom part of the interposer, you add the more than 3,300 solder balls, and then you flip chip it onto the printed circuit board, you do the reflow, you do the fiber attach, and you put everything in a mechanical housing. Now you see that this is not a straightforward packaging flow, but it's built to support this very large number of electrical connections which you need if you want to prototype very complex photonic integrated circuits. Now, of course, then you still need the electronics, so that means that you need to interface your photonics on the printed circuit board with driver electronics. The more electro-optic elements you're using, the more driver electronics you need, and the more complex your software becomes. So we've built, to support these programmable photonics, also the software framework that matches the circuit layout with the circuit models, with the circuit configuration routines, and access to the driver electronics, all from a single central software interface. So when we develop programming routines, for instance, based on these graph representations, so like to automatically identify routing paths through the mesh, we can do that directly in the software and download that configuration also directly into our hardware. Now, these algorithms can be quite complex because the larger the mesh becomes, the more difficult and the more computationally intensive it becomes to find optimal solutions. Luckily, with these graph libraries, we can reuse quite a lot of expertise from the world of network routing, etc. For instance, this example here gives the situation of a splitter tree, a 1x6 splitter tree, but with different boundary conditions. In the left, we want to optimize the splitter to use the minimal number of optical gates, while on the right, we want to split as quickly as possible to make sure that our optical power in each gate is as low as possible, so we suffer the least possible from nonlinear losses like to photon absorption. You can also configure more complicated circuits. For instance, this is a collaboration we had with MIT where they developed an optimization routine to dynamically optimize the configuration of the mesh to perform or implement any given transfer function, and do that starting from different starting conditions. Now these are some examples, but it's basically just to illustrate that if you want to build these programmable photonics, you need more than just a photonic chip. Programmable photonics is about the whole software stack, from the photonic chip to the electronics, the software, the optical interfaces, and then the electrical and microwave interface as well, so all the packaging. So you need to bring everything together, ideally in a quite compact package with all the hardware interfaces and the fiber pigtails and the drivers in the package. And then of course you can choose to put the light source on the chip, but most likely the light source, at least in the beginning, is going to be off chip. Now this is just half of the problem. As I mentioned, next to the hardware, you can only have a programmable system if you also have the software layers. So that means adding a user interface and a programming library that allows the user to define configurations, to calibrate the system, to implement feedback loops, to automatically route or filter your light, and eventually also debug what is going wrong in your circuit. Very similar as what we today expect from programmable electronics. Okay, if we manage to bring all of that together, we get this kind of general purpose programmable photonic chip. What can we do with this? Well, just some examples. You could, for instance, use it to implement an optical transceiver, like a parallel single mode fiber transceiver. That's very simple. You assign 4 fibers as outputs, 4 fibers as inputs. You come in with a laser, send it to 4 of these modulators, and then the modulators you route to the fibers. And the receiver is even simpler. You just connect 4 fibers to 4 detectors, and you have a transceiver. But at the same time, if you want a different type of transceiver, like for instance a transceiver that operates on WDM, you can come in with 4 lasers, use the mesh to define ring resonator filters to multiplex these 4 ring resonators with each with their modulated signal into a single fiber, and then send that out. While for the incoming light, you can define a similar filter bank to demultiplex the 4 wavelengths, each to their own photodetector. So this is not crazy. This is basically just using the capabilities of tunable elements in photonics. You can do more than transceivers, of course. You can, for instance, build a switch. You just assign 8 input, 8 output fibers, for instance, and then the routes that the fibers need to connect to one another. And these can be redefined on the fly to basically implement any kind of combination of inputs and outputs. You can also go beyond communication applications, like for instance build a spectrometer that can be implemented as a bank of ring resonators. Or you can do a microwave photonics filter, like for instance coming in with your laser, implementing microwave modulation onto your laser light, and then implementing, of course, also your filters, filter bank inside your photonic mesh, which can be done in the form of ring resonators or Mach-Zehnder interferometers. Now these are just some examples. Essentially what you can do with this chip is mostly limited by the creativity of the user. Now, does this give us the single chip that can basically do everything we want? Well, in a way, yes. It can handle a lot of functions, combine optical and microwave functions. It's flexible to program, but it's also going to be a large chip. So it might be expensive, it might have somewhat higher loss than a dedicated chip, and it might have higher power consumption. But it has a lot of benefits. First of all, if you take an off-the-shelf chip, your development time for a new application becomes much, much lower because your time to market is shorter. You can also upgrade your chip, so you can update the firmware and give it a longer lifetime with more functionality. And also because it's in software, there's a lot more people that can actually make use of this. And potentially you can address a much larger market. So with this story, I'd like to kind of capture what programmable photonics is all about. It's a world that is still very much moving and that's only just started. But the potential is huge because you can use these chips for optical and microwave processing for a variety of applications. Because they're programmable, they're off the shelf, they could speed up adoption of photonics dramatically, just like FPGAs have sped up the adoption of electronics. We're still early days. There's only a few demonstrations of such programmable photonic circuits, and there's still a lot of technological challenges. We don't have the ideal optical gate yet, and hopefully somewhere in the future someone will come up with a mechanism to tick all the boxes and all the requirements of the optical gate. There's a lot of software and algorithms that still have to be invented, but it's a very interesting space to work in. Now with that, I would just like to wrap up by thanking all the people who have in one way or another contributed to all this material that I've shown, also the funding and the projects that have been supporting this work. And with that, I would like to wrap up this presentation. Thank you.